Welcome to part 3 of a 5-part R&A's deep dive series,
The Genesis Project, creating an e-commerce site.
the assembly protocol.
If you've ever watched your server utilization spike to like 99% during a massive product drop, and you just hold your breath hoping the architecture holds.
Oh yeah, sweating while the fans are just screaming in the server room.
Right, exactly. Well, this is exactly the system you are relying on in that moment. As the original researchers behind the Genesis project, my partner and I are dissecting the foundational architecture required to build a massive, fault-tolerant e-commerce platform from the ground up.
Yeah, because we were looking at the relationship between the operational command, which is the physical local servers running the operation, and the network, which is the outward expansion of your digital empire.
And, the reality is you cannot expand outward until you have absolute control inward, right?
Exactly. Before our platform can push, a single product image across a network to a customer's browser, we have to establish dominance over the local machine. Code isn't just thrown onto a hard drive randomly.
No, not at all. It exists within this ruthless, highly structured hierarchy.
Right. It's built on 3 technical pillars. So at the base, you have system software, which is the overarching operating system.
The supervisor, basically.
Yeah, the supervisor. Then sitting on top of that is application software, which for our Genesis project includes the actual storefront portal, the inventory databases, the CRM.
Right.
And finally, there is embedded software.
Which is really the silent workhorse of any physical fulfillment operation. Embedded software doesn't live on our primary server racks.
Right. It's out in the physical world.
Exactly. This is the hard-coded logic burned directly into application-specific integrated circuits, ASICs.
Right, the ASICs.
Yeah, these are inside your warehouse barcode scanners or, the programmable logic arrays running the automated conveyor belts.
And they have incredibly narrow parameters. Right? They just execute one specific mechanical task with near zero latency.
Right. But looking at this entire hierarchy introduces I think it's one of the most fascinating systems implications in computer science. The Supervisor Paradox.
Oh, this is where the engineering gets super philosophical. Because if the operating system is the ultimate authority managing all the physical hardware, the memory modules, the CPU cores, the storage arrays, but the OS itself is technically just a piece of software living in memory.
Who manages the manager?
Exactly. Who manages the manager? How does the OS protect itself from being overwritten by the very applications it is supposed to be supervising?
Right. Well, it does so through physical hardware-enforced isolation. Think about how a machine actually wakes up.
Okay.
The moment power hits the motherboard, a tiny foundational piece of the operating system called the resident monitor, or the core kernel, is loaded directly into a heavily protected sector of RAM.
And it just stays there.
Right. It never leaves. It stays resident.
So, if the operating system is the brain of our e-commerce platform, the resident monitor is essentially the autonomic nervous system.
Oh, that's a great way to look at it.
Right. Because, I don't have to consciously think to keep my heart beating or my lungs expanding. The autonomic system handles that baseline survival.
Exact.
And the application software, the shopping cart, the search bar, those are the conscious thoughts. They're complex and constantly changing, like deciding to pick up a coffee cup.
Yeah, and taking that autonomic analogy a step further, the resident monitor doesn't just quietly run in the background. It violently protects the vital organs.
Violently?
Yeah. It utilizes what we call protection rings. The resident monitor operates in ring 0, which is also known as kernel mode. It has unrestricted God-level access to the physical hardware.
Okay, so the core kernel is in ring 0. Where are the applications?
The conscious thoughts, your storefront applications, are quarantined way out in ring 3, or user mode.
Oh, wow. Meaning, if the shopping cart application encounters a bug and, say, tries to execute a command that would overwrite critical system memory,
It physically cannot do it.
it just hits a wall.
It is stopped at the silicon level. The CPU sees a ring 3 application attempting a ring 0 instruction and instantly triggers a hardware trap.
Hardware trap. That sounds intense.
It is. The resident monitor stepped in, isolates the failing application, kills the process, and dumps the error log. And it does all of this while the rest of the server just keeps breathing.
Right, because if we didn't engineer that strict ring-level isolation into the Genesis project, just a single user inputting, like a corrupted credit card string, could crash the entire server cluster.
The whole thing would just drop offline, revenue drops to 0.
Which brings us to the active daily operations of the operational command. Because surviving a crash is one thing, but how does the OS organize the absolute chaos of 1,000 users browsing simultaneously.
Right, the day-to-day management.
Yeah. This is the domain of resource allocation. The OS is executing three massive mandates here. First, peripheral management, which is handling the driver handshakes with external storage and load balancers.
Right.
Second is memory management. And third is job management, specifically time slicing.
Well, let's dissect memory management first, because that is the defensive wall protecting your revenue stream.
Okay, let's get into it.
So when a user logs in, the server spins up a session. That session obviously requires active RAM. But the OS doesn't just hand the application a physical memory chip.
Right. It doesn't say, here's your hardware.
Exactly.
Yeah.
It uses virtual memory and paging. It creates an illusion for the application, providing it with this nice contiguous block of virtual memory addresses.
But under the hood, the OS is actually chopping that data into uniform chunks, right?
Yeah, pages.
Pages, right. And it scatters them wherever there is free physical space across the RAM modules. And then it maintains this highly complex page table to track where everything actually lives.
Exactly. And the crucial business implication here is security through compartmentalization.
Security, how so?
Well, because the OS acts as the absolute middleman translating those virtual addresses to physical ones, the shopping cart application literally cannot see, let alone access, the physical memory space where the highly secure payment gateway is processing a transaction.
Ah, I see. So if a malicious script somehow injects itself into the shopping cart,
It is blind. It's trapped within its own virtual sandbox. The bleed is completely contained.
that compartmentalization is vital. But let's look at the processing side of that equation. Job management and the concept of time slicing, which is often called the ghost in the machine.
It really is an illusion.
It is. Because to a customer looking at their screen, it appears that our server is running the product database, processing their specific payment, and updating global inventory at the exact same time.
Right, simultaneous.
But the CPU is physically incapable of multitasking in that way. It is dedicating a microscopic fraction of a second, a time slice, to the database, then switching to the payment gateway, then switching to the inventory log.
Right, it's executing sequentially.
Yeah, but switching so violently fast that to human perception, it creates the illusion of simultaneity.
It is a brilliant orchestration, but it does introduce a massive vulnerability that we really have to engineer around.
Okay, well, let me challenge the efficiency of that orchestration, my co-host. Because if the CPU is constantly stopping one task, saving its state, loading the state of the next task, and executing over and over again, doesn't the act of switching itself waste processing power? I mean, if 10,000 people hit the site during a flash sale and the OS tries to time slice 10,000 processes, at some point, isn't the manager doing more work than the workers?
Oh, absolutely. You've just described a catastrophic failure state known as thrashing.
Thrashing.
Yeah, because context switching carries a real computational overhead. Every time the CPU switches tasks, it has to flush its registers and pull new data from the cache.
That takes time.
Right. So if the system is overloaded, it spends more CPU cycles simply switching between tasks than actually processing the transactions.
Oh, wow. So the whole thing just bogs down.
The entire server grinds to a halt, even though the CPU is technically running at 100% capacity.
Wait, so how do we prevent a runaway process, say like a complex tax calculation, looping infinitely from monopolizing the CPU and pushing the system into thrashing?
Wow.
Because if the CPU is entirely focused on that one runaway thread, how does the OS even get the power to step in and stop it?
That's the beauty of it. It doesn't rely on software for that. It relies on physics.
Physics, you mean hardware?
Yeah. The motherboard contains a physical quartz crystal oscillator ticking millions of times a second. This is the hardware clock. So we configure the OS to set a strict timer for every single time slice. When a process is given the CPU, the clock starts ticking. When that timer hits 0, the hardware physically sends an electrical interrupt signal directly to the CPU's pins.
It physically forces the CPU to stop executing the current thread.
Exactly. The CPU has no choice. The electrical interrupt overrides whatever that runaway tax process is doing, forces the CPU to save the state, and hands control back to the resident monitor in ring 0.
That's incredible.
Yeah, and then the OS looks at the queue, realizes the tax process is hogging resources, deprioritizes it, and gives the next time slice to the inventory update. The interrupt is basically the emergency brake that ensures no single process can ever hold the hardware hostage.
Man, that physical architecture is what makes a local machine bulletproof.
Hmm.
We have the resident monitors secured in ring 0, memory strictly partitioned through paging, and hardware interrupts ruthlessly managing the CPU time slices.
The operational command is solid.
It is solid. But an impenetrable server sitting in a data center is useless if it cannot move data outward, right?
Right. Nobody can buy anything.
Exactly. We must transition from the OS to the network. We have to look at the topology that connects the empire.
Yeah, because the physical layout of the network dictates how efficiently we can scale. For the Genesis project, we bypass older ring or bus topologies entirely.
Right. We build strictly on the Star Topology standard.
That's right.
So picture a massive wheel. You have a central node at the hub of the wheel, and all the individual servers, external gateways, and workstation connections radiate outward along dedicated cables, the spokes.
Right.
And the inherent value of the Star Topology is compartmentalized fault tolerance.
Which is huge for us.
Huge. If a fiber optic cable is severed, or a specific database node suffers a catastrophic hardware failure, it only kills that one spoke. The central node simply recognizes the dead link and dynamically reroutes traffic to the redundant backup nodes on the other spokes.
The network survives.
Exactly.
Right.
But the true performance of a Star topology depends entirely on the intelligence of that central node.
Oh, yeah. And early networks, and shockingly, even some poorly audited modern setups, attempt to use a piece of transmission hardware called a hub at the center.
Ugh. Using a hub for an e-commerce platform is architectural malpractice.
It really is.
Let's visualize the data flow here.
Yeah.
Imagine our network is a high-volume trading floor, and the central node is a courier. A hub is essentially a courier walking onto the floor with a bullhorn.
A bullhorn. Perfect analogy.
Right. When a piece of data arrives, say, a customer requesting to securely load their cart, the hub doesn't know where the cart server actually is. So it takes the data packet and blindly duplicates it, blasting it out at maximum volume to every single port on the entire network.
Right, which means every single server, whether it handles payments, images, or inventory, receives that packet.
Just noise everywhere.
Yeah. And they all have to use precious CPU cycles to open the packet, check the destination address, realize it isn't for them, and drop it. It is a staggering waste of bandwidth and processing overhead.
So we replace the hub with a highly intelligent switch.
Right.
The switch replaces the bullhorn with targeted, discrete delivery. And how does it do that? Because a switch actively learns the network geography. Inside the switch is a piece of highly specialized memory called a CAM table content addressable memory.
Which is key.
Right. Every physical network card in our servers has a unique, hard-coded MC address. When the server sends its very first packet, the switch reads the source MC address and permanently maps it to the specific physical port it came from.
So it builds a dynamic map of the entire operation.
Exactly.
So when that customer requests their cart data, the switch looks at the destination MC address, queries its CAM table in a fraction of a millisecond, and creates a temporary dedicated electrical circuit only between the gateway and the specific cart server.
And the rest of the network hears nothing.
Nothing. The bandwidth is entirely preserved.
And, preserving bandwidth isn't just about speed. It's about preventing the physical destruction of data. Let's look at the mathematical impossibility of scaling a hub. Because a hub blasts data everywhere simultaneously. If two servers try to talk at the exact same moment, the electrical signals physically collide on the copper wire.
Right. They literally crash into each other.
Yeah. The voltages spike, the data is corrupted, and both packets are destroyed.
And this triggers a protocol called CSMA-CD, Carrier Sense Multiple Access with Collision Detection.
Basically a fancy way of saying they notice the crash.
Right. The servers detect the voltage spike on the wire, realize their data was destroyed, wait a random number of milliseconds, and try to transmit again.
But during a massive flash sale, the sheer volume of simultaneous requests in a hub network means those retransmissions just collide with new traffic.
Right, which triggers more retransmissions.
Exactly, and it cascades into a broadcast storm. The collision rate approaches 100%, and the network functionally collapses under its own weight.
Which is why a switch is so vital, because it entirely eliminates collisions. Each port on a switch is its own isolated collision domain.
And eliminating collisions allows us to implement advanced transmission modes to manage the immense traffic spikes. We configure the network for full duplex communication.
Right, meaning data can flow in both directions simultaneously on different frequency channels or wire pairs, much like a divided highway.
But for the Genesis project, the true optimization lies in time division duplexing, or PDD.
Oh, TDD is amazing.
It is. It's a fascinating mechanism for handling asymmetrical traffic because in an e-commerce environment, data flow is rarely equal.
No, almost never.
Right.
Yeah.
If a user is downloading a heavy 4K video rendering of a product, we are pushing massive amounts of data out to them while they are only sending tiny packets of acknowledgement back to us.
Exactly. So TDD monitors the queue depth of the network buffers in real time. Instead of dedicating a fixed 50-50 split of the bandwidth for uploading and downloading, it dynamically alters the time slices allocated to transmission versus reception.
That is so smart.
Yeah. If the outgoing queues are overflowing with video packets, TDD shifts the timing advance, dedicating perhaps 80% of the millisecond time slots to transmitting and only 20% to receiving.
Man, it essentially moves the concrete barrier on the highway in real time,
Mhm.
opening up 4 lanes for outbound traffic and leaving 1 lane for inbound, adjusting frame by frame as the load shifts.
Yes,
The network physically breathes and flexes to accommodate the pressure of user demand.
because designing rigid systems just guarantees they will shatter under scale. The architecture must be organic, reactive, and ruthlessly efficient at the microsecond level.
Which brings our design into full focus. Today, we secured the foundational bedrock of the Genesis project.
We really did.
We started deep within the silicon, mapping how the resident monitor uses hardware-enforced ring-zero isolation to protect the autonomic functions of the machine.
Right.
We explored how the operating system utilizes virtual memory paging to quarantine applications, and how it relies on the physical quartz clock to trigger hardware interrupts, preventing runaway processes from trashing the CPU.
Kept the local machine safe.
Exactly. And finally, we expanded out to the Star Topology network, replacing the chaotic collisions of a hub with the precise cam table routing of a switch, governing the massive data flows through dynamic time division duplexing.
We have engineered a platform capable of handling staggering complexity without buckling. But, as you look at the systems governing your own digital operations, I want to leave you with a final thought on where this architecture is heading.
Oh, what's that?
Well, we have spent this deep dive discussing how to efficiently allocate resources, CPU time, memory pages, network bandwidth, the moment a user demands them. But the horizon of system architecture is predictive resource allocation.
Predictive. Like allocating resources before the demand actually occurs.
Precisely. Imagine integrating machine learning models directly into the resident monitor. Models that analyze the micro movements of a user's cursor on the storefront, the dwell time on a specific product image, the historical conversion rates of their demographic.
Oh.
Right. What happens to our network topology when the overarching system becomes so incredibly tuned that it preemptively spins up database connections, loads secure payment gateways into physical RAM, and shifts the TDD bandwidth allocation entirely based on the statistical probability of a purchase?
Before they even do anything.
All before the customer has even clicked the buy button. What does the system look like when human intention becomes an executable network command?
That is wild to think about.
Thank you for joining us, and we look forward to continuing this journey with you.
Keep exploring. Expand your mind.